And I'm very happy to adjust if you would like to adjust. But my thought, our goal is to get ourselves ready for a quiz on Monday, right? So I was going to make time to go over the homework if you would like to do that. The answers are up there. I just pulled them from the book, so they're right there. I've got a couple of ranking tests that I would like to go through. I would like to have a little bit of a conversation about the collisions lab. I think that most of the people in this class were at least successful in getting your data and making your graphs, but if not, we'll have a conversation about that. And then I just pulled some more questions. These are from the end of the chapter, just more practice questions. So my thought was after we go through the homework and do our ranking tests together, that I would just give you guys some time to work. If you don't want that, if you feel like you're ready to move on, like you've got this stuff and you want to code, then we can keep going. I've got other things we can do. But this is kind of where I was getting a sense that maybe would be good for today. Does that sound like an okay plan to start with? Okay, awesome. But you guys let me know if there's something that you want to change or whatever. I'm happy to adjust. So homework questions, I guess we'll start there. I would like for you, please, to put your labs away for right now. We will have time to talk about those later, and we will do we'll get there, but I want your brain to be here so that we can all do this together. Yes, ma'am.
Can you go over page 13?
Number 4, for sure. Absolutely. Yeah. And I printed off some more of these sheets. So if you would like another one, or if you would like more, just come on up and grab them if you'd like them. I printed off a bunch. And I know that I promised you guys that I would post them on Canvas last night, and then I got home and got busy and blah, blah, blah. I did post them, and it was late, so I apologize for that. Life goes. So, and so now if you want it, there are lots of them, or there's one of them up there that you can print as many as you would like. So, Leanne, you had suggested that we look at number 213, number 4, this one. Is that right? Okay. So I'm going to go ahead and start with that one. If you don't have a textbook in front of you, I would encourage you to get one just so that you've got it, access to it, so that it's easy to look at here. And then, so I'm going to do page 213, number 4. So it looks like there's a dump truck. I'm just going to go ahead and read this one. It says there's a dump truck with a mass of 5.5 times 10 to the 5th kilograms. That's big when loaded, and it's 2.3 times 10 to the 5th kilograms when empty. Suppose that 2 such trucks, one loaded and one empty, crash into one another at a monster truck show. Full disclosure, I've never been to a monster truck show. Do they often crash dump trucks at monster truck shows? Is that a thing? I don't know. I mean, I'm not like opposed to monster truck shows. I've never had the opportunity. That's just kind of exciting. Okay. Trucks are supplied with special bumpers that make the collision almost perfectly elastic. So what does that mean? Are they going to stick together or bounce apart? Bounce apart. Elastic means they're going to bounce apart, right? If the trucks hit each other at equal speeds of 5 meters per second, and then the empty truck recoils to the right with a speed of 9.10 meters per second, what is the velocity of the full truck after the collision? Okay, so that's a lot of information, but I think with this chart, we can probably get this figured out pretty well. So our 2 objects are what and what?
An empty truck and a loaded truck.
Indeed. So there's an empty one and a loaded up one. Okay. So it says the empty truck is 2.3 times 10 to the 5th kilograms. They're going to crash into each other. What is the initial velocity of the empty truck? What does it say there? I'm going to have you guys read it, because part of doing these problems is just parsing out what the story says. What is the initial velocity of the empty truck? They're 5 meters per second, right? Yeah. Do we know, so if they're both moving at 5 meters per second like this, are they ever going to collide? I got one here, 5 meters per second.
No.
No. So that means that they've got to be going in opposite directions, which means that one of the velocities has to be what? Has to be negative. Yeah. It doesn't matter. I'm gonna make this one just regular, not negative, positive, I guess I could say. And so we can find the initial momentum. I'm gonna let maybe this half of the room do that one. And just to kind of expedite the process, the side over here, my left, so your right side, we're gonna do the loaded truck is 5.5 times 10 to the 5th kilograms. Its initial velocity, then we'll say, is negative 5 meters per second. So now if everybody has a calculator out, we should make this pretty quick here to find the initial momentum for the empty truck and the initial momentum for the loaded truck. So it's literally just mass times velocity, mass times velocity.
It does not matter if we switch the negatives around.
It does not matter. No, your answer will just say that the other one is negative in the end, right? But that, as long as you stay consistent in all of your assignment of negatives and positives, it's fine. So my friends over here, did you find the initial momentum of the empty truck? Did you guys find the loaded truck? Emma says, this is a new thing for me. I'm learning. I did put the video up, but I don't know if I tagged it or not. So I don't know if you were looking at it or if you were not like in the mode of physics. I will put it up. So it just kind of walks through exactly what we're doing.
Okay.
Yeah, that'll help out. But you can follow along with us now too. The idea, I made this little chart thing just to kind of help us keep everything organized.
I see.
Yeah. All right. Ben, did you get the initial momentum for the empty truck?
I got 1,150,000.
Wow, that's a lot. Can you tell me that in scientific notation? So 1 point something times 10 to the something?
That would be 1.15 times 10 to the 4th.
10 to the 4th? 6th? 6th, I think. Yeah. Kilogram meters per second. And those of you over here, did you guys get a momentum for the loaded truck? What'd you get?
That's right.
Well, give it a shot.
27,000. No. Yeah. Is that
So 2.7?
2,750,000?
Let's do scientific notation because that makes
2.7 times 10 to the 6.
that seems reasonable. So let's talk about, just before we do anything else, let's talk about what does it mean to be a reasonable answer. Look at this. It's 5 times 5. What's 5 times 5? 25, right? So very big ballpark. This answer is going to be something like 25 times 10 to the 5th. Are you with me there? You've got 5 times 5 and you've got a 10 to the 5th. So it's going to be something around 25 times 10 to the 5th, something a little bit more. And since it's 25 times 10 to the 5th, that means it's going to be like 2.5-ish times 10 to the 6th. Okay? So you can know if you're on the right track, know if you've got like you totally screwed up or not, just by like kind of reasoning out this. Same with this one. If I've got 2 times 5, that's going to be something, it's going to be 10, right? A little bit more than 10 because we've got this 3 here. So a little more than 10 times 10 to the 5th. That's going to be like 1.1 times 10 to the 6th. Okay? This is like the thinking piece, right? All right. Do the masses change after the collision? Yes or no?
No.
No. Silly Miss Carbling. Of course they don't. Oh, it should be negative. Absolutely. Indeed. All right. So the masses are the same. What do we know about the velocities after? So it says it recoils. What does to recoil mean? Do you know? I'm going to take it. Yeah, there's like a kickback or a bounce off. So if the empty truck was moving in the positive direction and it recoils, and remember it said that this is an elastic collision. What do you know about the direction of the motion after the collision? Is it going to be positive or negative?
It says to the right.
It does, but it hasn't told us if this one moves to the right or left at the beginning, which is the thing that's why I'm trying to like kind of parse this out. I think it's going to be a negative velocity though. Does that make sense? Since it's going backwards, it's bouncing off the other direction. So I think it's going to be a negative 5 meters per second. Is that right? No, 9.1. I was going to say that didn't sound right. And then then we can find that final momentum. What do we get for the final momentum for the empty truck? Say that one more time.
2.09.
And does that seem reasonable? You've got like a 2 times about a 10, right? So it's going to be about 20 times 10 to the 5th. 20 times 10 to the 5th would be 2 times 10 to the 6th. So that seems like a reasonable answer. Oh, man. We forgot to do the total before. Let's do that real quick. I'm sorry. I didn't mean to lead us astray. 1.15 times 10 to the 6th kilogram meters per second is the initial for the empty. And negative, purple please. Negative 0.7 times 10 to the 6th kilogram meters per second are the initial numbers. Is the initial momentum positive or negative? Without even plugging anything, the calculator should be able to tell us.
Maybe. Oh, man.
Yours is positive because you're the other way, right?
Yeah.
The way we have it right now is going to be negative, right?
Yeah.
What's the value? Negative what? You guys should be able to figure that out without even doing anything. 2.7 minus 1.15?
Yeah.
What is it? Oh, friends, do we need to go back to 3rd grade math? Come on, you can do this. 2.7 minus 1.15. You got this. Borrow. Like you can do that in your head, right? You should be able to. What's that? I think it should be 2.65, shouldn't it? Did I write it down wrong?
No.
Huh? 7 minus 1, but you got that 5, you got to borrow.
No. When I multiplied the negative 5 times 5.5, I got 2.75.
I totally missed you.
Right there.
Here you got 2.75.
2.75.
I see what you're saying. Okay.
But yeah.
Okay, that makes me happier then. Okay. So then you get 1.6. That's okay with me. Are we okay? Not intending to confuse you. I hope I'm not. The loaded cart has a mass of 5.5 times 10 to the 5th. Do we know the final velocity? Nope, that's our big question mark. So the final momentum for the loaded cart is 5.5 times 10 to the 5th kilograms times V final or VB final. Negative 2.09 times 10 to the 6th kilogram meter per second plus 5.5 times 10 to the 5th kilograms times VB final. Oops. Set this one equal to this one. Did you notice I put the little equal sign in there? That was the upgrade that I did last night. You're welcome. I thought it was nice. Negative 1.6 times 10 to the 6th kilogram meters per second is equal to negative 2.09 times 10 to the 6th kilogram meters per second plus 5.5 times 10 to the 5th VBF. Can you solve that for the velocity? Right now we're subtracting 2.09 times 10 to the 6th. How do you undo that subtraction? Add it to the other side. Okay. And then we need to get the 5.05 or 5.5 times 10 to the 5th away. Right now it's being multiplied, so how do you undo the multiplication? Divide. Go ahead and do that. I got your back on the physics, but I think you should be able to do this algebra at this point. VB final. 0.89 meters per second to the left. Does that match what you all got? Hopefully, and if I messed up, let me know. Get it?
Yeah, your negatives were easier though. I had to do negative x, and then you can't forget to do the negative x.
The negative, yeah.
I would
Yeah.
definitely do that on the test.
So the thing that I would encourage you to do, and the thing that we're going to do next, is if you draw the graph, you'll be able to tell if you've screwed it up.
Yeah.
Yeah. So you'll notice the 2 upgrades that I made, actually 3 since I showed you guys this yesterday. I added the equation at the top. I added your equal sign because that just makes me happy. And then I also gave you a little axis. What do you think that axis is for? I want you to graph the picture. Graph the situation. It'll make sure that you understand. It'll also be a good double check to make sure that you didn't make a silly mistake. So graph the displacement versus time for both the empty and the loaded truck on that axis. Okay? So the empty truck is moving in a positive direction with a slope of 5. How's the slope for the loaded truck going to compare? It's going to be the same, except it's going to be negative instead, right? So it's starting definitely from a different location. That's where the collision happens. And then let's think about what's going to happen here. So the empty truck goes from having a positive 5 to a negative 9. How's that slope, that steepness going to compare? Is it going to be more steep or less steep? More steep. It's going to be in the negative direction, but more steep. And the velocity for the purple car, the loaded one, is going to be positive, but very, very, very slightly positive. And it might be helpful as you're doing this to draw arrows. I don't know if that helps you or not. It kind of helps me to see what's going on. Okay. Yeah.
Can you go through the math of getting 0.89?
Sure. From here?
Yeah.
Absolutely.
We can drop out the exponents.
Yep. Well, yeah. Hold on just a second. Let me move that down. Okay. So I would add 2.09 times 10 to the 6th. Add 2.09 times 10 to the 6th. So that's going to give me, what, 1 point something something. Or excuse me, 0.49. 0.49 times 10 to the 6th is equal to 5.5 times 10 to the 5th times VBF. And then we're going to divide by 5.5 times 10 to the 5th. Yeah, I wouldn't.
You can't just do 4.49 divided
You can't because this one, that one should be a 10 to the 5th. That's why.
Because then you get to
Yep.
0.089.
Yeah, because your factor is off. So if you're going to get lazy, if you choose to become lazy when you're doing these problems, the maximum amount of laziness that you could have would be to not write the units.
Yeah.
But you have to, like if you have a big numbered thing, you have to have those exponents because those mean things, right? The 10 to the 5th and the 10 to the 6th mean that this one has more zeros than this one. This one's a bigger number than this one. Yeah. The other option, Isaac, would be to say that these are 10 to the, like this would be like 20.9 times 10 to the 5th.
Yeah.
And this is 5 times 10 to the 5th. Like if that makes your head happy, then that's fine. It's a little like funny, but you could, everybody's different, right? Everybody makes choices. So how are we doing?
I did not get 0.89.
You did not get 0.89?
Maybe it's something to make up.
So 0.49 times 10 to the 6th divided by 5.5 times 10 to the 5th.
Yeah.
That's what I did, but I'll do it again. 0.49 e to the 6th divided by 5.5 e to the 5th.
You just got it.
So do you do a little e thing or no? What do you do? What do you think?
I do. So this is what I do.
Oh, yeah, nice. Is that what you said? Like that good?
0.49 times 10 to the 6.
Uh-huh.
Divided by.
You can.
Parentheses,
You
you're
can,
fine.
yeah, or just do that and then you have to do divide by and then you have to put those in parentheses.
So which part of parentheses?
Because it doesn't do PEMDAS. It just literally reads.
So you did 0.49.
E means times 10 to the
So E is 6.
Yep, and I put that in parentheses. This is what I did. I had 0.49 e to the 6th, all parentheses,
Okay.
divided by.
Okay.
Does that make sense?
I don't know how to put point.
All right, my dears. How are we doing? Are we okay? Feel like you can do these problems? Ish.
I think the scientific notation.
Yeah. I heard, what did you say?
What? Oh, I just said that I can do the problems. I'm just worried about the graph.
Okay, so we need to practice that, right? Sweet. All right, we can totally practice it. Tell me, is it just like, does it intimidate you, or is there like something about it that doesn't make sense?
No, it makes sense once it's there, but I can't like think of it for myself.
Oh, okay.
Like it makes 100% sense when like we did it in class, but then like trying to do it on my own, it doesn't.
So what I'm going to encourage you to do when you're doing these practice, like today and this weekend, is to draw your pictures, right, on like all of these guys. You don't have to do all of them. But honestly, if like the graphing is the thing that's stressing you out, then just take these answers, fill out your chart, take the answer and fill it in, and then just draw the graph from that.
Okay.
And then if you want to come in and like check in with me on Monday morning and be like, are these right? Then I can totally look at them.
Okay.
Does that sound good? Yeah.
Thank you.
Yeah.
I was like,
And like today too in class, we have time too. All right. So before we move on, I hear that lunch is about to switch now. Are there any of the other homework questions that you are eager to go over? If there are ones, like if you get stuck later, let me know. I would like to do a couple of quick, not for our class. Like we're about halfway done. No, I'm sorry. I misspoke. Like it's loud out there. That's what I mean.
we could have the 09 on the other.
Yeah.
That's fine.
Oh, okay, gotcha. No, sorry. I didn't mean to confuse you. My tummy is hungry because it's, Friday and it's late, but whatever. I can handle it. Okay, I want to do a couple quick conceptual questions to make sure that we're feeling good about that. Okay, because again, the math part of it is that's just like the underlying. I want you to know the physics. Like I want you to understand. So we're gonna do that quick, and then we'll talk about the lab and give you some more practice and whatever. We'll go from there. All right, quick. Some ranking tasks to look at. So here's one.
Do we need quiz?
Are these going to have a quiz or any tests?
I don't know.
Do you need quiz?
Would you like a board? Go get a board. Do we need a board? He needs a board. He's trying his head. All right. Here we go. You got two colliding carts. It's as if you've done this in a lab or something. Two carts traveling in opposite directions are about to collide. Ah! The carts are identical in size and in shape, but they carry different loads and are traveling at different speeds. The carts stick together after the collision. There's no friction involved. The task asks you to rank the speed of the two-cart system after the collision. So the plug and chug approach would be to literally solve each of these 4 problems. If you want to do that, you can. You can also kind of pull yourself out of that box and see if you can think about a way to figure this out without having to do that. Okay? I'm going to let you think for a minute because I don't want to tell you how to do it. I'll let you think, and then we'll discuss in a minute.
Yeah, but
There's no negative.
do you get it? Yeah.
All right. In the interest of time and physics opportunity, Ben, can you explain this to us?
So I said that they are all zero
Okay.
because there's a velocity going in a negative direction and a velocity going in a positive direction,
Okay.
and all of their all their momentums are the exact same if you calculate them.
Do you guys understand what he's saying? So what's the momentum of the left-hand cart in A?
That would be 10,000.
10,000. Does that make sense? 20 times 500 is 1,000, or excuse me, 10,000. And the momentum, oops, I'm on freeze, so you can't see my lovely 10,000. The 25 times 400, also 10,000.
Phenomenal job, Ben.
Okay. That's the most complicated of them. In B, you've got 20 times 400, and you've got 10 times 800. In both cases, they are 8,000. One of them's negative, I suppose we should probably acknowledge that, right? So this is 8,000 and negative 8,000. In C, everything is 10,000 again. And in D, we've again got, what is that? That's going to be 16. So we did that. That's all well and good. How does that lead you to your answer, though?
Well, if you add them up, they go to zero.
Okay.
And so the answer is they're all zero. And you said rank the speed, and there's no speed if the momentum is zero.
So if the total momentum is 0 and the two carts stick, if the total momentum is 0 and the two carts stick, then they're going to stop. If the two carts didn't stick, then that wouldn't be the case. Are you with me there? That would be different. Because then they would bounce off and we could do the math to figure out what was going on there, but we're not going to do that right now. But because they stick, absolutely, the total momentum is 0, which means that we got nothing. That makes sense? We could, I mean, it's a little hard to do it because it's hard to launch cars at the same speed or at specific speeds. I did have a group at some point, I don't remember if it was this class or AP or the other class, but where they were doing that. Like they got it so that they go and it would stop. It was cute. I think they did one of their collisions based on it, so it was kind of neat. All right. Here's another one. So this one's a little bit funny, and it's not a ranking task, but it's kind of a thinking task. And we're going to take just a few minutes on this one, just because I want to make sure that we get through other things too. It says, in case a metal bullet penetrates into a wooden block. In case B, a rubber bullet with the same speed and the same mass, so that means it has the same initial momentum, bounces off an identical wooden block. So the same situation, except that one is an elastic collision and one is an inelastic collision. This is a big thinker problem, but it's awesome. The question is, will the speed of the wooden block after the collision be greater in case A, greater in case B, or the same in both? I'll let you guys think for a couple minutes. What do we say? Is it A? Is it B? Are they the same? What do you argue? Somebody wrote something on their board. It says greater in case B. Somebody else wrote something on their board. It says same. Anybody else writing on their board? They want to, I guess I'm thinking number 1, case A. Just asking. Same. Okay. All right, let's talk it through. Help me out. Why did you say what you said?
Just the force now on the box is the same in both of them. Like one bounces off and one sticks, but the amount of force that's pushing on the box is the same.
The amount of force, the force on the box by the bullet, is that what you
Yeah.
mean? Like,
Yeah.
is the same in A and in B?
Yeah,
How do you know that?
because their initial where is it? It says that
They have the same initial speed?
Yeah. Yeah, is the same in so when it's hitting it and pushing the box forward, one sticks and one bounces off, but like the initial push was equal in both of them. So it moves the same distance.
What do you guys think?
I agree.
Do you agree with that?
I agree. Yeah.
Go.
I was just gonna say, like, freshman year, they used to give us these, like, mini pancakes for lunch, right? And there was this, like, so we used to, like, pull up the textbook and, like, put it on the table, and then someone would throw the mini pancake at it, and sometimes it would stick, and sometimes it wouldn't. But it never tipped over if it bounced off or stuck. So it always, like, stayed the same.
This was freshman year.
Yeah, freshman year. Do you guys remember those mini pancakes?
What?
Yes. The drum.
Are related.
Bad freshman kids. Jeez.
Related to the lab.
It was a physics experiment.
I guess. Yeah, for sure. So the question is the force of the bullet on the block the same in both cases? Can I ask you a question, a follow-up question to that? Is the force of the block on the bullet the same in both cases? If the forces of the block on the bullet is the same in both cases, is the acceleration of the bullet the same in both cases?
Yes, it's the same mass.
So acceleration means change in velocity over time, right? It also means F net over m. So you're saying they have the same mass, they have the same net force. Let's talk about the change in velocity, though. The velocity of the bullet before is, I'm just going to make up a number. Let's say +3. Is that okay? I'm just picking something because I don't know. Is it going to speed up or slow down when it hits the block? Or stay the same?
When it hits the block,
When it hits, in case A,
it'll be slow.
it's going to get slower a little bit, maybe?
We related to the lab, like the graph right here.
You did this one, right?
Yeah, and it hit it. It was going 38 meters per second.
Uh-huh.
And then it went all of a sudden it went to 20 meters per second.
Yeah.
And then when it was in the elastic, it all that speed that when it hit, it
Uh-huh.
transferred it all into that, and then it stopped, and then it kept going. So in the elastic one, it was going 30, and then it kept going 30, and in the inelastic one, it was going 30, but then it dropped to down 20.
Okay. I think I understand what you're saying. So you feel like this is an accurate depiction, picking random numbers.
Yeah.
The initial velocity here is 3. What's the final velocity?
It'll be negative.
It'll be negative something, right? I don't know if it's going to be big or small or whatever. I'm just going to pick some random. Well, I'm just going to say it's negative. We know that it's negative because it's bouncing off. So I'm just kind of working through what you're saying. The acceleration of the bullet is the same in both cases. Acceleration is change in velocity over time, right? So the change in velocity, this one goes from 3 to 1. So that change in velocity would be -2. So this one has a change in velocity, change in velocity of -2. What's the change in velocity of this one? We don't know for sure, but what does it have to be? It's got to be something more than -2, right?
Yeah.
Because it's going negative something. So it's got to be more than -3. Does that make sense? I'm going to say that the change in velocity here, whoa, has to be greater than -3. If the change in velocity is not the same, is the acceleration the same? If the acceleration isn't the same, is the force the same? You with me there? Do you understand what I'm saying?
Only thing that's the same is the mass.
The only thing, well, the initial velocity is the same and the mass is the same. Yeah, yeah. I love the idea here. I love the idea that you're saying. I like that the forces are the same, but we just have to be careful. And so I wanted to kind of chew into that because I don't want you to have a misconception. The forces here and here for case A and case B are different. And the reason that I know that, the reason that my little radar went off was like, because I see that the change in velocities are different. The force of the block on the bullet is the same as the force of the bullet on the block in this case. You with me there? Third law. Force of the block on the bullet on the block in case B is the same, but these two forces are not the same. You guys had circled this one or said this one.
In case B.
Okay, why? I don't know if that's right. Well, I know, but
Well,
I'm not gonna.
I related it to the lab or whatever.
Okay.
So when I was like when we looked at the graph right here,
Uh-huh.
if you do the carts, they're the same mass.
Mm-hmm.
In the gray cart, you push first, and it had an initial 38.22 centimeters per second, and it hits the other one, and they stick, like the first one right
Mhm.
there. It then went 20.93 centimeters per second,
Okay.
so it dropped. And then in the elastic one, the gray car was going 31.54 centimeters per second, and when it hit that one, it stopped, or it went back.
Mm-hmm.
And then it transferred all that speed into the green car, which was going then 31 centimeters per second.
What do you guys think? Does that make sense to you? Can I draw a picture that might be helpful? I don't know if this is going to be helpful or not. This is how my brain thinks of it. In case A, we have a certain amount of momentum. It's that momentum. This is the momentum initial. How does the momentum initial compare to the momentum final? What do they have to be?
Equal.
They have to be equal, right? In this one, they're both moving in this direction. You with me there? So that means that the momentum of the bullet and the momentum of the block have to add up to this. Are you with me there? In case B, we have the same amount of momentum to start. What do you know about the momentum of the bullet? Which way is it going? It's going the other direction, right? So in order to add our little arrows together, we've got one that's going this way. Here, I'm going to try and figure out how to do this. It's going, I don't know where to put it. Here, I guess. That's the momentum of the bullet. Actually, no. Here's what I'm going to do. Start from the same spot. So the total momentum for the block has to be this big in order to add up to the same thing. Oops. Does that kind of make sense? This is a deep question. This question won't be on your quiz, but the principle of this question I think is really interesting. The gut feeling part of this question is really interesting. So anyway, is that kind of okay? We've got a negative value, so this has got to be a really big positive value to make up the total that we've got to start. Whereas this one, we've already got some started here, so we just have a little bit left that we have to add in case A. Okay? Okay, where are we at? We've got about 8 minutes. Let's go back here for just a second to the list of things to do. So collisions lab, just a couple of quick things about the collisions lab. If you have successfully taken data on Logger Pro for the collisions lab, if you have questions for me on what you need to do, I am very, very happy to answer them. And I can do that now in the last few minutes, okay? But I'm looking for something filled out here, and filled out here, so I can imagine what your collisions look like. And then a conclusion based on your data and referring to your data. Okay, it says, write three or two, I don't know, 2 to 3 sentences, drawing conclusions based on your experiment. Use specific data to support your claims and discuss whether your findings support is momentum conserved. Okay? If you've got your data, awesome. If you are, for whatever reason, the technology is messing you up, it's whatever. I spent my 3rd period today making a set of data based on somebody's videos, okay? So I'm going to put this up on Canvas during lunch today. So there's collision 1, there's a collision 1. This might not be your collision 1, but it is a collision 1, okay? With the masses and then information there, collision 2, and then collision 3, okay? So if you need data, it's there. It'll be up during lunch today. I'll put it up so you've got it, okay? If you have this done and you want to give it to me today, fantastic. If you would like to hold on to it and work on it this weekend, that's fine with me. I'm not going to grade them this weekend, so you can have it and I'll collect them on Monday. Does that make sense to you all? Does that seem reasonable?
That's only if you have, don't have your own data.
Correct. Yeah. So because in my other class, I had a few people who had technical issues. And so it was like, they couldn't get their videos in and whatever. I mean, I don't know that this data is amazing. I just borrowed videos, but yeah, I mean, it's pretty. So hopefully the numbers work out. I don't actually know, but I would imagine they are probably decent. So anyway, I will put this up during lunch so you have access to it if you need it. Okay. So right now, you've got a few minutes. I want you to do physics. You can either work on that collisions lab if you would like to or if you need to, or you can work on these problems. These are not required problems, but these are probably you need to do some more practice between now and Monday. So there are some ones to work on. All right? You got just a couple minutes. Use those minutes wisely. Don't waste my time. Don't waste your time, friends.